Marie Skłodowska was born on November 7, 1867, in Warsaw, Poland, except Poland didn't officially exist at the time. The country had been partitioned among Russia, Prussia, and Austria, and Warsaw was under Russian imperial control. This political reality would shape Maria's entire childhood and early adulthood. Her father, Władysław Skłodowski, was a teacher of mathematics and physics at a gymnasium. Her mother, Branislawa Skłodowska, was the principal of a prestigious girls' school. The Skłodowski family belonged to the Polish intelligentsia, educated, cultured, patriotic, but living under foreign occupation that actively suppressed Polish language, culture, and identity. Maria was the youngest of 5 children, born into what should have been a comfortable middle-class existence, but the family's fortunes were precarious. Her father's outspoken Polish nationalism cost him positions and promotions. He made disastrous financial investments trying to supplement the family income, losing much of their savings. The Russian authorities were systematically removing Polish teachers from positions of influence, replacing them with Russians who would enforce Russification policies. Teaching Polish history was forbidden. Speaking Polish in schools was punishable. Russian language and Russian Orthodox religion were imposed. In this atmosphere, the Skłodowski home became a sanctuary of Polish culture, books in Polish, conversations about Polish history and literature, a determined preservation of identity in the face of empire. But beyond political oppression, the family faced personal tragedy that would mark Maria forever. When she was 8 years old, her oldest sister Zofia died of typhus. 2 years later, her mother died of tuberculosis, a disease she had been fighting for years. The loss of her mother was devastating. Maria, just 10 years old, lost the warm, nurturing presence that had been the center of the household. Her father, overwhelmed by grief and financial pressures, became emotionally distant. Maria threw herself into her studies, finding in academic excellence a kind of refuge. She was brilliant, graduating from gymnasium at 15 with a gold medal, top of her class in every subject. But what next? Maria desperately wanted to continue her education, to attend university and study science. She had a particular fascination with her father's physics demonstrations. He had been forced to sell most of his physics equipment after losing his teaching position, but he still owned a few instruments, locked away in a glass case like precious relics. Young Maria would stare at these mysterious objects, the barometers, the electroscopes, the glass tubes, imagining the experiments they could perform, the secrets of nature they could reveal. She wanted to be a scientist, to understand how the physical world worked, to make discoveries. But women weren't admitted to the University of Warsaw. Russian authorities certainly weren't going to educate Polish women in science. The path forward was blocked. The solution came through a pact between Maria and her older sister Branislawa. Branislawa wanted to study medicine in Paris, where women could attend university. Maria wanted to study physics and mathematics, but neither had the money for tuition and living expenses. So they made a deal. Maria would work as a governess in Poland, sending money to support Branislawa in Paris. When Branislava finished her medical degree and established herself, she would support Maria while she studied. It was a plan that would require years of sacrifice and patience. Maria was 17, and the University of Paris seemed impossibly far away. For the next 6 years, from 1885 to 1891, Maria worked as a governess for wealthy Polish families. The work was often lonely and frustrating. She was educated, intelligent, ambitious, yet reduced to tutoring children and managing households. But she never stopped learning. She read physics and mathematics textbooks in her spare time, teaching herself advanced topics. She joined a flying university, an illegal educational initiative where Polish intellectuals gave secret lectures to students, particularly women, who were barred from official education. These clandestine classes were risky. Discovery could mean arrest or exile, but they kept Maria's mind sharp and her spirits up. The low point came when she was working as a governess for the Zorawski family. She fell in love with Kazimierz Zorawski, the family's eldest son, who was studying mathematics at the University of Warsaw. The feeling was mutual, they became engaged. But Kazimierz's parents were horrified that their son would marry a penniless governess. They forbade the marriage, and Kazimierz, lacking the courage to defy his family, broke off the engagement. Maria was heartbroken, humiliated, and furious. The experience hardened her. She realized that she couldn't depend on marriage to escape her circumstances. She needed to rely on herself, on her own abilities and determination. Finally, in 1891, at age 24, Maria had saved enough money, and Bronislawa was established enough in Paris to make the move. Maria left Poland for France, not intending to abandon her homeland, but understanding that only in Paris could she pursue the scientific education she desperately wanted. She enrolled at the Sorbonne, taking the French version of her name, Marie Skłodowska. She was older than most students, spoke French with a heavy Polish accent, had gaps in her preparation due to her years as a governess, and was one of only a handful of women in the science faculty. But she had waited too long and sacrificed too much to waste this opportunity. She studied with ferocious intensity, living in a tiny, unheated attic room, often going without adequate food to save money, frequently studying until she fainted from exhaustion and cold. It was brutal, but in 1893, she graduated first in her class with a degree in physics. A year later, she completed a second degree in mathematics, graduating second in her class. Marie Skłodowska had finally become what she'd dreamed of being, a scientist. In 1894, Marie faced a new problem. She needed laboratory space for research on the magnetic properties of steel, work she'd been commissioned to do by the Society for the Encouragement of National Industry. But she had no access to a proper laboratory. A Polish colleague suggested she meet Pierre Curie, a respected physicist who worked at the Municipal School of Industrial Physics and Chemistry in Paris and might have access to laboratory space. The introduction was arranged, and Marie met Pierre for the first time in the spring of 1894. Pierre Curie was 35 years old, 8 years older than Marie. He came from a family of doctors but had turned to physics, showing exceptional talent in experimental work. Along with his brother Jacques, he had discovered piezoelectricity, the phenomenon where certain crystals generate electric charge when mechanically stressed, and had invented the electrometer, a sensitive instrument for measuring small electric currents. Pierre had a reputation as a brilliant experimentalist, but also as something of a dreamer, more interested in pure research than in career advancement. He had never married, living with his parents, and dedicating himself entirely to his scientific work. The meeting between Marie and Pierre was transformative for both. Pierre was immediately struck by Marie's intelligence, her dedication to science, and her seriousness of purpose. Marie found in Pierre not just a potential collaborator but a kindred spirit, someone who understood her passion for research, who took her seriously as a scientist, who saw her as an intellectual equal rather than as a curiosity. They began working together in the laboratory, and Pierre began courting Marie with unusual intensity. He wrote to her, "It would be a fine thing to pass our lives near each other, hypnotized by our dreams, your patriotic dream, our humanitarian dream, and our scientific dream." But Marie was conflicted. She had planned to return to Poland after completing her studies, to contribute to Polish science and culture, to fulfill what she saw as her duty to her oppressed homeland. Marriage to Pierre would mean staying in France, abandoning those plans. She returned to Warsaw in the summer of 1894, uncertain about her future. But Poland offered her nothing. Women still couldn't hold academic positions, the Russian occupation was as oppressive as ever, and the scientific opportunities were minimal. Pierre wrote to her repeatedly, pressing his case, arguing that they could accomplish more together than apart, that science transcended national boundaries, that their partnership would be extraordinary. In July 1895, Marie returned to Paris and married Pierre Curie in a simple civil ceremony. She wore a dark blue dress, practical, reusable for laboratory work, instead of a traditional white wedding gown. There was no church service, no grand celebration, just a brief legal formality followed by a bicycle tour of the French countryside. It was thoroughly unconventional and perfectly suited to both of them. They moved into a small apartment near the School of Physics and Chemistry, and Marie officially became Marie Curie, though she would use both her maiden and married names throughout her career, sometimes signing papers as Marie Skłodowska Curie. The marriage was a true partnership both personally and scientifically. They shared household duties, they discussed science constantly, they supported each other's work. In 1897, Marie gave birth to their first daughter, Irene. Marie hired a nurse to help with childcare and returned to the laboratory as soon as possible. She was determined that motherhood wouldn't end her scientific career, a radical position at a time when married women, particularly mothers, were expected to abandon professional ambitions. Pierre's father, Eugene Curie, a retired doctor, moved in with them to help care for Irene, providing crucial support that allowed Marie to continue her research. By late 1897, Marie needed to choose a topic for her doctoral thesis. She had been following the recent discovery by Henry Becquerel of mysterious rays emitted by uranium compounds, rays that could expose photographic plates even in darkness, rays that seemed to be a property of the uranium itself rather than the result of any external energy source. This was deeply puzzling. Where did the energy come from? What were these rays? Most physicists found the phenomenon interesting but not particularly important, just another curious property of a rare element. But Marie saw opportunity. This was unexplored territory, a phenomenon that no one really understood, perfect for doctoral research. She began systematically investigating these uranic rays, using Pierre's electrometer to measure the ionization they produced in air, a far more precise method than the photographic plates Becquerel had used. She tested every uranium compound she could obtain, measuring the intensity of radiation from each. And she discovered something remarkable. The intensity of radiation depended only on the amount of uranium present, not on the chemical compound it was in, not on temperature, pressure, or any other physical condition. This suggested that the radiation was an atomic property, coming from the uranium atoms themselves. It was the first evidence that atoms, long thought to be indivisible and unchanging, might have internal structure and might be capable of transforming. Then Marie made an even more surprising discovery. She tested pitchblende, a uranium ore, expecting it to be less radioactive than pure uranium compounds since it contained other elements diluting the uranium. Instead, pitchblende was more radioactive, several times more radioactive than could be explained by its uranium content alone. There could be only one explanation. Pitchblende contained another element, unknown to science, that was even more radioactive than uranium. Marie had discovered not just a new element, but a new phenomenon, radioactivity itself, a term she coined to describe this mysterious property. The hunt for the new element became the Curie's obsession. Pierre was so intrigued by Marie's discovery that he abandoned his own research on crystals to work with her. They made a formidable team. Marie's determination and systematic approach combined with Pierre's experimental ingenuity and theoretical insight. They worked in a converted shed at the School of Physics and Chemistry, a miserable space, unheated in winter, stifling in summer, with a leaky roof and inadequate equipment. Marie would later describe it as a cross between a stable and a potato cellar. But it was where they could work, and they threw themselves into the task with absolute dedication. The challenge was enormous. Pitchblende contains dozens of elements in small quantities. The new radioactive element, if it existed, was present in tiny amounts. To isolate it, the Curies would need to process tons of pitchblende ore, separating and testing each fraction, following the radioactivity. This wasn't delicate laboratory work with precise instruments and pure chemicals. This was industrial-scale chemistry, involving huge vats of boiling solutions, backbreaking physical labor stirring and mixing, handling dangerous chemicals in a poorly ventilated shed. The Austrian government, which controlled uranium mines in Bohemia, agreed to provide the Curies with tons of pitchblende residue, the material left over after uranium extraction, which was normally just discarded as waste. The Curies paid for transportation, and soon their shed was filled with sacks of brown ore residue. Marie would haul the heavy sacks, pour them into enormous iron pots, boil them with various chemicals, filter and precipitate, repeating the process over and over, each iteration concentrating the radioactive element a little more. It was exhausting, dangerous work. They had no understanding of the health hazards of radiation, worked without protective equipment, and were constantly exposed to radioactive dust and fumes. In July 1898, just months after beginning their search, the Curies announced the discovery of a new element, which they named polonium after Marie's beloved Poland. A gesture of patriotism and a way to remind the world that Poland, though partitioned, still existed in the hearts of its people. Polonium was intensely radioactive, far more so than uranium, but the Curies weren't done. The pitchblende residues still contained another radioactive element, different from polonium. They continued their painstaking work, processing batch after batch, concentrating the radioactivity. In December 1898, they announced the discovery of a second new element, radium, named for the intense radiation it emitted. Radium was even more radioactive than polonium, and it had an unusual property. It glowed in the dark with a faint blue-green light, a ghostly luminescence that fascinated everyone who saw it. The Curies would return to their shed at night to see their preparations glowing eerily in the darkness, like something supernatural. It was beautiful and mysterious, and it proved that radioactivity wasn't just an abstract phenomenon measured by instruments. It was visible, tangible, real. But announcing the discovery wasn't enough. To convince the scientific community, the Curies needed to isolate pure radium, determine its atomic weight, and characterize its chemical properties. This meant processing even more pitchblende, refining the separations, producing ever-purer fractions. Marie took charge of this effort, spending 4 more years in grueling chemical work. She processed 8 tons of pitchblende residue, working often alone in the shed, stirring boiling solutions with iron rods nearly as tall as she was, working in clouds of acid fumes, covered in chemical burns and calluses. Pierre later wrote, "I remember the day when I came to see her. I found her stirring a boiling mass with an iron rod nearly as large as herself. She was dressed in her old dust-covered and acid-stained smock." Finally, in 1902, Marie succeeded in isolating 1/10 of a gram of pure radium chloride from several tons of pitchblende. It was enough to determine radium's atomic weight, 226, and place it definitively in the periodic table. The discovery was complete, the evidence overwhelming. Marie had found 2 new elements and had proven that atoms could spontaneously transform, emitting energy in the process. It was one of the most important discoveries in the history of chemistry and physics. The scientific community began to recognize the magnitude of the Curie's achievement. In 1903, Marie successfully defended her doctoral thesis, Research on Radioactive Substances, becoming the first woman in France to earn a PhD in physics. The examiners declared it the greatest contribution to science ever made in a doctoral thesis. The same year, the Curies, along with Henry Becquerel, were awarded the Nobel Prize in Physics for their work on radioactivity. Marie was the first woman to win a Nobel Prize, a historic achievement that brought her international fame. But the recognition came with complications. Initially, the Nobel Committee had planned to award the prize only to Pierre and Becquerel, omitting Marie despite her crucial contributions. One of the committee members mentioned this to Pierre in a letter. Pierre responded with outrage, insisting that Marie had been the driving force behind the discovery of polonium and radium, that she deserved recognition at least as much as he did, and that he would refuse the prize if she weren't included. The committee relented, adding Marie to the award. It was a small victory against the pervasive sexism of the era, but it required Pierre's advocacy. Marie's own work wasn't considered sufficient to guarantee her inclusion. The Nobel Prize brought fame and some financial relief. The prize money helped the Curies improve their working conditions and reduce their teaching loads, but it also brought unwelcome attention. Journalists wanted interviews, society wanted to meet the famous woman scientist, invitations and requests poured in. The Curies, who valued privacy and focused work time above all else, found it overwhelming. Marie particularly struggled with her newfound celebrity. She wanted to be known for her science, not for being a woman in science, and she found the constant attention exhausting and intrusive. Worse, both Pierre and Marie were beginning to experience health problems: exhaustion, chronic pain, strange burns on their hands that wouldn't heal. They attributed these to overwork and chemical exposure, never suspecting that radioactivity itself might be dangerous. They kept samples of radioactive materials in their pockets, on their desks, by their bedside to admire the glow. They had no concept of radiation safety, no understanding of the cumulative damage being done to their bodies at the cellular level. The very discoveries that would make them famous were slowly killing them. The years following the Nobel Prize were productive, but increasingly difficult. Pierre finally received a professorship at the Sorbonne in 1904, with Marie appointed as his laboratory chief, the first official academic position she held. In 1904, their second daughter, Eve, was born. The family settled into a routine: research, teaching, raising their daughters, all while managing the health problems that were becoming more severe. Pierre's pain was sometimes so intense he could barely function. Marie suffered from exhaustion and what we would now recognize as radiation sickness. Then, on April 19, 1906, catastrophe struck. Pierre was crossing the Rue Dauphine in Paris during a rainstorm, distracted and in pain. He stepped behind a horse-drawn wagon and was struck by another wagon coming from behind. He fell under the wheels, and his skull was crushed. He died instantly, at age 46. Marie was 38 and suddenly a widow with 2 young daughters and no clear future. The scientific partnership that had defined her adult life was shattered. The man who had loved her, supported her, believed in her when almost no one else did was gone. Marie's grief was overwhelming and private. She didn't cry at the funeral. She didn't speak about Pierre's death, even to close friends. She poured her anguish into her journal, writing to Pierre as if he could still hear her. They filled the coffin, they put on the cover, they fastened it. I saw nothing, I heard nothing, I heard the sound of the nails, it hurts. They filled the grave and put sheaves of flowers on it. Everything is over. Pierre is sleeping his last sleep beneath the earth. It is the end of everything, everything, everything. But Marie had to continue. She had 2 daughters to support, research to complete, a legacy to uphold. The Sorbonne offered her Pierre's professorship, an unprecedented decision to appoint a woman to such a position. On November 5, 1906, Marie gave her first lecture to a packed amphitheater filled with students, colleagues, and curious Parisians who wanted to see the famous Madame Curie. She walked to the podium and began speaking, picking up exactly where Pierre's last lecture had ended, as if no time had passed, as if the continuity of the work itself could bridge the gap left by his death. It was a powerful statement. Science continued, knowledge accumulated, individual lives ended, but the pursuit of understanding endured. Marie threw herself back into research with even greater intensity. Grief drove her, but so did determination to prove that she could stand on her own scientifically, that her contributions hadn't been merely auxiliary to Pierre's. In 1910, she published a massive treatise, over 900 pages, titled Treatise on Radioactivity, summarizing everything known about the subject. The book was a monument to the field she had essentially created, establishing her as the world's leading authority on radioactivity. The same year, she finally succeeded in isolating pure radium metal, not just radium compounds, but the element itself, a silvery white metal that glowed in the dark. It was an extraordinary technical achievement, requiring heating radium compounds to extreme temperatures using electric currents in a vacuum. In 1911, Marie was nominated for a second Nobel Prize, this time in chemistry, for the isolation of pure radium and the determination of its properties. It should have been a moment of triumph. Instead, it became one of the most painful episodes of her life. Just as the Nobel Committee was deliberating, a scandal erupted in Paris. Marie had been having an affair with Paul Langevin, a former student of Pierre's who was married but separated from his wife. Langevin's wife had obtained some of Marie and Paul's letters and threatened to publish them unless Marie ended the relationship. When Marie refused to be blackmailed, Madame Langevin leaked the letters to the press. The scandal was enormous. French newspapers ran sensational stories about the affair, portraying Marie as a foreign homewrecker who had seduced a married Frenchman. The fact that she was Polish, that she was a woman in a traditionally male field, that she was already famous and successful, all made her a target. Anti-Semitic and xenophobic attacks appeared in the press, despite Marie being Catholic, not Jewish. Crowds gathered outside her home shouting insults. She received hate mail and threats. The scandal was so intense that a member of the Nobel Committee wrote suggesting she not come to Stockholm to accept the prize. Marie was furious. She wrote back, essentially telling the Nobel Committee that the prize was for science, not for her personal life, and that she would absolutely attend the ceremony. In December 1911, she traveled to Stockholm with Irene and Bronislawa and accepted the Nobel Prize in chemistry, becoming the first person ever to win Nobel Prizes in 2 different sciences. It was a historic achievement, a vindication of her scientific stature. But the personal cost had been enormous. The scandal, combined with the stress of the previous years, damaged her health severely. She suffered a nervous breakdown after returning from Stockholm and spent months recovering in a sanatorium, hidden under a false name. Slowly, Marie rebuilt her life and career. The scandal faded, though the experience had hardened her further, made her even more private and guarded. She returned to work, to directing her laboratory, to training the next generation of researchers in radioactivity. When World War I broke out in 1914, Marie found a new mission. She recognized that X-rays could be invaluable for locating bullets and shrapnel in wounded soldiers, helping surgeons operate more effectively. But most field hospitals didn't have X-ray equipment. Marie organized a fleet of mobile X-ray units, radiological cars that became known as Little Curies. She equipped vehicles with X-ray machines and dynamos powered by the car engines, then drove these units to field hospitals near the front lines. She also trained operators, gave lectures on radiology, and personally performed X-ray examinations of wounded soldiers. Irene, just 17 when the war began, worked alongside her mother as a radiological assistant. Together, they established over 200 permanent and mobile X-ray installations, training 150 radiological technicians. These units examined over 1 million wounded soldiers during the war, saving countless lives and limbs. Marie's work during the war was heroic, but also dangerous. She was constantly exposed to X-rays with no protection, adding to the radiation damage her body had already sustained from years of working with radioactive materials. Her hands showed radiation burns and lesions. Her blood showed abnormalities. But she never complained, never slowed down. When the war ended in 1918, Marie was exhausted, but could take satisfaction in having contributed significantly to the war effort, and in having proven, once again, the practical value of radioactive and radiological research. After the war, Marie's focus shifted to building institutions and training researchers. In 1909, even before her second Nobel Prize, the University of Paris and the Pasteur Institute had agreed to create a radium institute, with Marie as director of the physics and chemistry section. Construction was interrupted by the war, but by 1918, the Radium Institute was complete, a modern research facility dedicated to studying radioactivity and its applications, particularly in medicine. Radium was already being used experimentally to treat cancer, and the institute would become a leading center for what we now call radiation oncology. Marie threw herself into building the institute into a world-class research center. She recruited talented researchers, secured funding for equipment, and created an environment where serious scientific work could be done. One of her most important recruits was her own daughter. Irene Curie had shown scientific talent from an early age, and Marie had always encouraged her. After the war, Irene became her mother's assistant and then a researcher in her own right at the Radium Institute. Mother and daughter worked side by side, just as Marie and Pierre had decades earlier. But there was a problem. Radium was extraordinarily expensive. Marie's laboratory had only about 1 gram of radium, the amount she had laboriously isolated from tons of pitchblende, and it wasn't enough for all the research projects she wanted to pursue. Radium had become commercially valuable for medical treatments and for making luminous paint, used on watch dials and instrument panels. But it was produced in the United States, and a gram of radium cost about $100,000, an impossible sum for a French academic laboratory in the economically devastated post-war period. Enter Marie Melloni, an American journalist and magazine editor. Melloni traveled to Paris in 1920 to interview the famous Madame Curie and was shocked to learn that the discoverer of radium couldn't afford to buy the element she had discovered. Melloni launched a campaign in the United States to raise money to buy Marie a gram of radium. American women contributed, seeing in Marie an inspiring figure who had overcome obstacles to achieve scientific greatness. In 1921, Marie traveled to America to receive the radium, presented to her by President Warren G. Harding in a ceremony at the White House. The American tour was exhausting. Marie was 53 and in increasingly poor health, but it was also validating. She was celebrated, honored, given honorary degrees from American universities, received by the president, and treated as a scientific hero. The trip raised awareness of her work and secured crucial resources for the Radium Institute. She would make a second trip to America in 1929, again organized by Melloni, this time to receive funding for radium for the institute being established in Warsaw in her honor. Throughout the 1920s, as Marie directed the Radium Institute, her health continued to deteriorate. She suffered from cataracts, probably caused by radiation exposure, which gradually dimmed her vision. Multiple eye surgeries provided only temporary relief. Her hands were scarred and burned from handling radioactive materials. She was frequently ill, suffering from what doctors couldn't quite diagnose: chronic fatigue, fevers, infections. We now know these were symptoms of radiation damage to her bone marrow and immune system, but in the 1920s, the long-term dangers of radiation were still poorly understood. Yet she continued working. In 1925, Irene defended her doctoral thesis on the alpha rays from polonium. In 1926, Irene married Frédéric Joliot, a talented physicist working at the Radium Institute. Marie welcomed Frédéric into the family and into the scientific collaboration. Irene and Frédéric would work together as a team, just as Marie and Pierre had, and in 1935, they would win their own Nobel Prize in chemistry for discovering artificial radioactivity, the ability to make stable elements radioactive through bombardment with particles. Marie didn't live to see this triumph, but she knew their work was important and was proud of their achievements. In 1932, both of Marie's great projects, the Radium Institute in Paris and the Radium Institute in Warsaw, were thriving, training researchers, making discoveries, treating cancer patients. Marie could see her legacy extending beyond her own discoveries to the institutions and people she had nurtured, but her health was failing rapidly. By 1934, she was seriously ill, suffering from fevers and weakness. Doctors diagnosed aplastic anemia. Her bone marrow was failing to produce blood cells. On July 4, 1934, at a sanatorium in the French Alps, Marie Curie died at age 66. The official cause was aplastic anemia, but the underlying cause was almost certainly prolonged exposure to radiation. She was buried in Sceaux, alongside Pierre. Her coffin was placed on top of his, reuniting them in death as they had been partners in life. The ceremony was simple, as Marie had requested. She had always shunned pomp and ceremony, but her death was mourned around the world. Obituaries celebrated her as one of the greatest scientists of the age, the first woman to win a Nobel Prize, the only person to win Nobel Prizes in 2 different sciences, a pioneer who had opened doors for women in science. In 1995, 61 years after her death, Marie Curie became the first woman to be interred on her own merits in the Panthéon in Paris, the mausoleum where France honors its greatest citizens. It was a symbolic recognition of her achievements, a formal acknowledgement that she belonged among the heroes of French and human intellectual history. But her real legacy isn't in honors or monuments. It's in the science she created and the doors she opened. Marie Curie's scientific contributions are enormous and enduring. She discovered 2 elements, polonium and radium, and proved that radioactivity was an atomic property, providing the first evidence of atomic transmutation and the first hints of the structure of the atom. This work laid the foundation for nuclear physics, leading eventually to the understanding of atomic structure, nuclear fission, and nuclear energy. When Rutherford and Bohr developed their models of the atom, when Fermi created the first nuclear reactor, when the Manhattan Project built the atomic bomb, all of this rested on foundations that included Curie's discoveries about radioactivity. The practical applications have been equally profound. Radium and radioactive isotopes revolutionized medicine. Cancer treatment with radiation therapy, first explored with radium, has saved millions of lives. Modern radiation oncology, nuclear medicine, and medical imaging all trace their origins to Curie's work on radioactivity. The X-ray units she developed during World War I were the beginning of battlefield medicine's use of imaging technology. Today, CT scans, PET scans, and other radiological techniques are routine, indispensable tools in diagnosis and treatment. But Marie Curie's legacy extends far beyond her scientific discoveries. She was the first woman to win a Nobel Prize, the first woman professor at the Sorbonne, the first person of any gender to win Nobel Prizes in 2 different sciences. Every one of these was a barrier broken, a precedent set, a demonstration that women could achieve at the highest levels of science. When female scientists faced discrimination or doubt, they could point to Marie Curie as proof that genius knows no gender. Yet this legacy is complicated. Curie became an icon, a symbol, often reduced to a simple narrative. The poor Polish girl who came to Paris, discovered radium, won 2 Nobel Prizes, all while being a devoted wife and mother. This narrative is inspiring but incomplete. It smooths over the difficulties, the years of brutal physical labor in the shed, the sexism she faced constantly, the pain of Pierre's death, the vicious scandal that nearly destroyed her, the radiation damage slowly killing her. It makes her story seem inevitable rather than the result of extraordinary determination in the face of enormous obstacles. There's also a darker aspect to Curie's legacy. She died from her work. The radiation that made her famous also killed her, and she wasn't the only victim. Many early researchers in radioactivity died young from radiation-induced cancers and other diseases. Factory workers who painted radium on watch dials suffered horrific illnesses. The radium girls who ingested radioactive paint while shaping their brushes with their lips developed bone cancers, anemia, and other radiation diseases. For decades, the dangers of radiation weren't properly understood or adequately communicated. Marie herself never fully acknowledged the dangers. She knew radiation could cause burns, she had them on her hands, but she didn't believe low-level, chronic exposure was harmful. She opposed safety regulations on working with radioactive materials, seeing them as unnecessary restrictions on research. It's hard to blame her. Radiation damage is insidious, delayed, and was poorly understood in her time. But her casualness about radiation safety, born of ignorance, contributed to underestimating its dangers for years. Modern physics has moved far beyond Curie's discoveries, but they remain foundational. Every nuclear reactor generating electricity, every smoke detector using americium, every cancer patient receiving radiation therapy, every PET scan revealing a tumor, all connect back to those years in the shed when Marie and Pierre Curie processed tons of pitchblende to isolate radium. The glowing element that fascinated them, that they kept by their bedside to admire, that Marie carried in her pocket, turned out to be far more dangerous and far more useful than they ever imagined. For women in science, Marie Curie remains a towering figure, though not an uncomplicated one. She blazed trails, but she also sometimes downplayed the obstacles she faced, perhaps to avoid seeming like she was complaining or asking for special treatment. She succeeded in a male-dominated field, but often credited Pierre more than herself, perhaps out of genuine modesty, or perhaps recognizing that crediting her husband made her achievements more acceptable to a sexist society. She opened doors, but was also used as an excuse. If Marie Curie could succeed, why can't other women? Ignoring the exceptional circumstances, abilities, and support she had. The Radium Institute she founded, now the Institut Curie, continues as one of the world's leading cancer research and treatment centers. The institute treats thousands of cancer patients annually and conducts cutting-edge research on cancer biology and treatment. It's a living legacy, directly descended from Marie's vision of applying radioactivity to medicine. Her daughter Irene and son-in-law Frédéric Joliot-Curie won the Nobel Prize in Chemistry in 1935. Her granddaughter Helene Langevin Joliot became a nuclear physicist. The scientific dynasty Marie founded continued for generations. Perhaps the most fitting tribute is this. When you ask schoolchildren to name a scientist, many will say Marie Curie. Not just a female scientist, a scientist. Her name has transcended the categories that sought to limit her. She's not just famous for a woman or famous for overcoming obstacles. She's famous for changing our understanding of matter and energy, for discovering elements, for pioneering a new field of physics. That was what she wanted, to be judged as a scientist for her work to speak for itself. The elements she discovered, polonium and radium, remain in the periodic table, permanent additions to the roster of nature's building blocks. Element 96, discovered in 1944, was named curium in honor of Marie and Pierre. It's a fitting tribute, a radioactive element created artificially through nuclear reactions, named for the couple who first understood that atoms could transform and release energy. Every time a nuclear physicist creates curium in a reactor, every time a chemist writes its symbol Cm in an equation, the Curies are remembered. Marie Curie lived through the transformation of physics from a science that seemed nearly complete to one in crisis and revolution. When she began her research in 1897, atoms were thought to be indivisible and unchanging. By the time she died in 1934, atomic structure was understood, quantum mechanics had been developed, and nuclear physics was revealing the tremendous energy locked in atomic nuclei. She was both a driver of that revolution and a witness to it, discovering phenomena that demanded new physics and living to see that new physics developed. She worked harder than almost anyone, sacrificed more, endured more pain and loss. She was driven by curiosity, by love of science, by determination to succeed in a world that said women couldn't be serious scientists. She made mistakes, underestimating radiation danger, sometimes being too proud to ask for help, perhaps working herself too hard. But she also achieved things that seemed impossible, broke barriers that seemed unbreakable, and left a legacy that extends far beyond her own discoveries to the countless people she inspired. When Marie Curie wrote in her journal to the dead Pierre, she said, "Pierre, my Pierre, you are there, calm as a poor wounded man resting in sleep, the head bandaged. Your face is sweet and serene, it is still you, lost in a dream from which you cannot get out. Your lips, which I used to call greedy, are pale and colorless. Your little beard is gray. One can scarcely see your hair because the wound begins there, and above the forehead, on the right, the bone that broke can be seen. Oh, how you have suffered! What a shock your poor head has felt. your poor head that I so often caressed in my two hands." This passage, so raw and painful, reminds us that behind the scientific icon was a woman who loved deeply, who suffered deeply, who experienced the full range of human emotion even while pursuing the most abstract and intellectual of goals. Marie Curie wasn't just the first woman to win a Nobel Prize or the discoverer of radium. She was a daughter who lost her mother young, a student who struggled financially, a wife who found in Pierre a true partner, a mother who raised two daughters while pursuing groundbreaking research, a widow who channeled grief into determination, a woman who refused to let society's limits define her possibilities. The shed where she discovered radium is gone. The gram of radium she isolated has long since decayed. Her notes and papers are still so radioactive they're kept in lead-lined boxes and can be consulted only with protective equipment. But her ideas, her discoveries, her example, these remain, radioactive in their own way, still emitting energy, still affecting the world around them, still inspiring new generations to ask questions, seek answers, and refuse to accept that any door is permanently closed to those with talent, determination, and courage.